Hi, everybody. Welcome to SFU Math 232, section 6.3, Applications of Diagonalization. So the last lecture, we learned how to find a similar matrix to a given matrix, which was diagonal. And then we saw right after that, that there is a method for finding the dominant eigenvector called the power method, which requires us to take powers of a matrix. So we're going to sort of be combining these two ideas, and we're going to learn how diagonalization is sort of helping us well, it helps us to take powers, and then we're going to see yet another example of this. Okay, so here we are, a little bit of vocabulary, and that this vocabulary will become clear as the lecture proceeds. So the key point here is that if we diagonalize a matrix, that makes computing the powers of the matrix easy. I mean, if I have some matrix A, and I want to find A to the 100. I mean, it is going to be painful, even in a computer, to multiply A by itself 100 times, particularly if A is a large matrix, 100 by 100 matrix, or 200 by 200 matrix. And then we're going to try to compute A to the 100. So what we're looking for is a method that makes that easier. And what makes that easier is diagonalizing A. So what we found in the last lecture, 6.2. So in 6.2, we found that we could diagonalize A. Okay, so keeping in mind A is the matrix that we wish to take the powers of, and we found we could diagonalize A in this manner. We could find a matrix P such that P to the -1 AP is D, and D is a diagonal matrix. So that this is the matrix we started with, A, and then we were able to find P using the eigenvectors, and then we can invert it, and then that will allow us to find D. Now let's take this equation, P to the -1 AP equals D, and let's multiply both sides by P on the left. So I'm going to go like this, P multiplying both sides of this equation on the left by P. So I've multiplied here on the left by P and here on the left by P. Then this combination here is I. So that leaves me with AP equals PD. And then I'm going to multiply on the right by P inverse. And then this guy here is also I. P times P inverse is the identity matrix. So that means that given this, I have that I can represent my matrix A as PD P to the -1. So once I have that diagonal matrix, I already have P and P to the -1. I can, if you like, factor A in this manner. Now, how does this help me? I'm bearing in mind what I want to do is compute what's in the back of my head here is I want to compute A to some power K. And that could be an onerous calculation. So I'm looking for a different way to compute that. So I claim, and I'm gonna actually prove this because it's easy to do. I claim that A to the K, which is what I want to calculate, is equal to P D to the K, P to the -1. That's my claim. I'm going to show you that that is true. Okay, so let's do that, and then I'll do an example. So we have already that A is equal to P D P to the -1. That is the case, in fact, when K is equal to 1. I mean, that would be A to the 1 here and D to the 1 there. Okay, so that we have already what's called, so we haven't done a lot of proofs. And so if you don't quite follow the proof reasoning behind this proof, don't worry about it. But it's so straightforward and it's kind of elegant. So I'm going to do it anyhow. But this method I'm going to use is called proof by induction. Proof by induction works by saying it's true when K is equal to 1. And then we're going to assume some arbitrary K over here. We're going to say, assume it's true here. That's not true over at say here at K. And then we're going to show that being true at K means that it's true at k plus 1. Then think about what this must mean. I could say it is true at k equals to 1. And then I'm showed you that if it's true when k is 1, it means it's true when k is 2. But then because I've showed you that if it's true at k, then it necessarily follows at k plus 1. Now I set k to 2. I'm like, see, it tells me that if it's true when k is 2, that means it's for sure true when k is 3. And then I use this reasoning again. I'm like, hey, if it's true when k is 3, that means it's true for k is 4. And all the dominoes just fall down. So what you want to basically do is push down the first domino, and then this reasoning of showing that when the kth case is true, it follows immediately that the k plus first case is true. That allows this first domino that you push down when it's true when k is 1 to knock down all the rest of the dominoes, and it's true for all values of k. That is your basic proof by induction. Now it's going to look like this. We show that it's true for the base case. That's when k is 1. Then we assume the result for k. And so k could be 1, k could be 10. We're assuming the result for k. Now we consider the k plus first case. Okay, let's take a look at that. A k plus 1. Well, that is actually a k times a. That's what rule of exponents. So let's write out what is a k. So I've assumed the result for k, which means I know that a to the k p d to the is equal to this. So I substitute that here. And then I multiply by a, this guy here. Like that. Okay, then what I see immediately is that I've got this situation here, and that is I. So I'm going to rewrite this as p d to the k d p to the inverse of p. Then I'm going to combine these two here, and that's going to be d k plus 1. So then I see that a to the k plus 1 is equal to p d to the k plus 1 times p to the minus 1. And that's the end of the proof. Okay, I set k equal to 2, set k equals to 1, it means k equals 2 is true. Set k is equal to 2, it tells me that k equals 3 is true. Then I've established 1, 2, and 3 are true. Then I say set k equal to 3, it tells me that k is 4 is true. You just knock all the dominoes fall down. Okay, so that is a proof. So this is the case. So look at how much easier it is going to be to find the powers of A if we have it factored in this manner, because when I have a diagonal matrix, let me just write down the diagonal matrix we're going to use in a sec. Here's a diagonal matrix. Okay. When I take, let me call that D because it is a diagonal matrix and it is going to be the one I'm going to use. If I want to take a power D to the 50 or something like that, that looks like this. Okay. It is very easy to take powers of a diagonal matrix because when you do the matrix multiplication, all you're doing is picking up, I mean, let's just do this so that we see 14, 0. So let me just square it. Okay, so now I'm going to take this row times this column. You see what happens. I get 14 squared. And then I take this row times this column like that down here, and I get minus 7 squared. And then the other ones, I'll have zeros in both places. So I've got this situation like that. Okay, so that just keeps happening. That's a square. That keeps happening. And so any power, this is it. So it's extremely easy to take powers of a diagonal matrix. That is not the case when you have a non-diagonal, when you have entries in these, when you have numbers outside of 0 here. When you have a non-diagonal matrix, that's not so easy. So that's where the power of this comes from. So let's take a look at the example from last lecture. We had just so I have the numbers, I can show you them. So we had last lecture, we had a matrix A, and it was this guy here, 11, 6, 9, minus 4. And we found that the matrix P, 2, 1, minus 1, 3, and then we inverted that matrix. So this is all lecture 6.2, the additional material like this, or diagonalizing matrix in section 6.2. Like that. And then we computed D, and it was this guy up here. In fact, I don't need to write it again. It's this guy right here, D. Okay, and that is, we had said that P to the minus 1, P to the minus 1, AP was equal to D with those matrices. Okay, now having rearranged, we are now here. We could rearrange this. We did rearrange it in general. So now we know that A, which is this guy, 11, 6, 9, minus 4 is, so I'm writing here, A is equal to P, D, P to the minus 1, like that. That is, A is equal to P, 2 minus 1, 1, 3, D, 14, 0, 0, minus 7, P to the minus 1. Okay, now my goal, let's just say, is to compute A to the 10. So A to the 10 is going to be P, D to the 10, P to the minus 1. And I can now simply write this out. I don't have to do a whole, I don't have to multiply A by itself 10 times. No, I will multiply P. I will have here 14 to the 10, that's a big number, and minus 7 to the 10, like that. And then I will simply multiply that by this guy here. Like that. Okay, and I'm done. So now I just do the 2 exponentiations of a number and then 2 matrix multiplications. And I have my answer. I do not do 10 matrix multiplications. So that is a key feature of diagonalizing, is that it makes computing powers easy. And we saw in the power method for finding the dominant eigenvalue that we had to compute the powers of the matrix. So it would make sense to diagonalize those matrices when computing the powers. Okay, here's another example, another application. So there's really no new math coming here. What we're doing is just showing an application of what we already know how to do. And there is some vocabulary here. We'll just say what that is. So first we have a dynamical system. What is a dynamical system? It's a finite set of variables whose values change with time. Okay, the value of a variable at a point in time is called the state of the dynamical system. And then the vectors composed of the different states is called the state vector. So let's just get some examples here. We could have a state as a celestial object's position. And then we could have a state vector, which consisted of the position of the Earth, the position of the moon, and the position of the sun. That would be a state vector, and it would be based on a certain time t, and it would change over time. Okay. Similarly, we could have a state being the population of a predator-prey system in a close environment. So our state vector then would be, for example, the number of rabbits at time t and the number of foxes at time t, and that will all change over time. Our state vector is the vector containing those 2 numbers, and then it changes that over time. It's a dynamic system. Okay, we could also have, actually market share might not be in our textbook. Let's just cross that out. We could have, for example, an idea of market share, percentage of the TV viewers for some type of TV channel. So we have, for example, how many people are watching CBC at time t, how many people are watching CNN, and oh no, how many people are watching Fox News? Okay, so we have 3 numbers, or in this case percentage, what percentage of the people are watching each one of these 3 stations, and that would potentially change over time. Okay, so what we're going to do is capture that information in a vector, and then we're going to see how to capture in a matrix how these things change over time, and then predict what like the predator-prey situation will look like sometime in the future, or what the viewership of your TV channels will look like etc. So in order to do this, we need just to get a few other things, which I think are, you already know. So let's just give an informal definition of probability. That's the number of successful experiments that you have divided by the total number of experiments. So the probability of obtaining heads by flipping a coin is 1 in 5, right? You have one time, that's a success. A head comes up once, and there's how many possible outcomes are there? There's 2. You could get heads or tails. So that's 1/5. And the probability of getting 5 on a dice is like 1 in 5. I'm sorry, 1 in 6. Now there's 6 faces on a die, and you throw it, and some number comes up, and the probability, if it's random, is 1 in 6. Okay, so that's what it is. A probability vector is a vector that has non-negative entries that add up to 1. Okay, so for example, for the dice, if you were thinking, oh, let's make a probability vector, let's call it x1, you would be thinking, okay, fine, there's going to be these numbers in here like this. There's going to be 1, 2, 3, 4, 5, 6 of them. There would be a probability vector where this guy, probability of rolling a 1, probability of rolling a 2, 3, 4, 5, and 6. All of them are probability greater than or equal to 0, and then the total is equal to 1. Okay, here's another probability vector. Looks like this, like that. There, it's totals up to 1. They're all greater than or equal to 0, and you could be thinking of this as like the percentage of students watching. What do we call it? CNN or CBC? CBC, and then this would be the percentage of students watching CNN, and then this would be the percentage of students watching Fox News. Okay, so you capture the state of your variables at a particular time t in this state vector. If we make a matrix whose columns are probability vectors, we call that a stochastic matrix. I like that word. Okay. If we have the situation where we have a dynamical system whose state vectors change, and they change only based on what the state vector was at the time immediately beforehand. So they change somehow. We're going to capture what this is, this matrix, but the state that the vector is in at time k+1 is only depends here on where it was 1 unit before at time k. It doesn't depend on k-5 or k-10 or some other state in the past. Okay. All right. This matrix here captures how the state vectors change. Okay, let's just see an example. I think this becomes pretty obvious when there's an example. Wildlife migration. So here we've got a situation where we've got some lion that can go in 3 different reserves in search of food. Now, somebody's been studying lions, and they realize that if a lion is in reserve 1 at some time t, there's a 50% chance he's going to stay there. That's what this indicates. 50% chance he's just going to stay there in reserve 1. There is a 30% chance he will depart for reserve 3, and there is a 20% chance he'll depart to reserve 2. Okay. Similarly, if that lion is here in reserve 2, there's a 20% chance he's going to stay where he is. There's a 40% chance he's going to move to reserve 3, and there's also a 40% chance he's going to move to reserve 1. Okay, so this is basically we have either a single lion or a percentage of the lions in the reserves, and we understand their movement patterns, and we can model this as a Markov chain with a transition matrix. Okay, so let me show you what the entries into the matrix are in this case. Each column is a probability vector, and each column has to add up to 1. So what we're going to do is we're going to look first at reserve 1. So the first column here is going to be looking at reserve 1. And we're going to say, if you're in reserve 1, what's the probability that you stay in reserve 1? Put that number here. If you're in reserve 1, what's the probability that you go to reserve 2? If you're in reserve 1, what's the probability that you go to reserve 3? There. So that is the column that indicates that we know is telling us what happens if you're in reserve 1, what happens in the next time state. Okay. Then we do the same thing for reserve 2. If you're in reserve 2, what's the probability that you go to reserve 1? If you're in reserve 2, what's the probability you stay at reserve 2? If you're in reserve 2, what's the probability you go to reserve 3? So this is reserve 2 right here. And then we're doing the column for reserve 3. If we're in reserve 3, now notice this is the first row. If we're in reserve 3, what's the probability of going to reserve 1? What's the probability of going to reserve 2? What's the probability of staying in reserve 3? There it is. Okay, that is a stochastic matrix. Each one of the columns is a probability vector. And now what we can do is use this to compute what happens over extended time periods. Okay, so let's just see how this works. We're at time t equals 0. Time equals t equals 0. And we know that the lion is in reserve 2. So what does x of 0 look like? Well, it's time 0. We know the lion is in reserve 2. That means he's not in reserve 1. It's a 100% chance he's in reserve 2, and he's not in reserve 3. We know where he is. He's in reserve 2. Okay, 100% chance. We see him. Okay, now we want to do what we want to do is I want to show you first. Let's look at at time t equals 1. So what we're going to say is whatever that is in this time t is in months. Okay. Okay. So in the next month, where is the lion going to be? Well, there's some probability he'll be in one of the, well, he will be in one of the 3 reserves, but with different probability. So let's look what happens at time 1. What we take is we take the transition matrix. We're computing x of 1. We take the transition matrix. And we multiply by where he is now. Okay, and what numbers are we going to get? Well, we're going to get 0.5. That is the first row times that column, and then the second row times that column, and then the third row times that column. Okay, there we get that guy right there. Hang on, let's try that again. We take the first row times the first column. It picks up this entry right here. Sorry about that. And let's do it again. I picked up the wrong entries. And then we take this row times that column, and the 1 picks up this entry here. And this one, I just copied the wrong column. Okay, there we go. Okay, let's look at that. Let's look back here. I'm going to erase this here. We know he's in reserve 2, right? And now we're saying at the next time count, where is he likely to be? Well, we know there's a 40% chance he'll be in reserve 1. That's exactly what this is telling us. There's a 40% chance he'll be in reserve 3, and there's a 20% chance he'll have stayed where he was. That's what this is telling us. This is a way that you can tell you've picked up you've got the entries into the matrix correctly. You could do the same thing. You could do the same thing starting with a lion that is in reserve 1, and then multiplying by this. Then you should pick up the numbers for reserve 1. Okay, but now that we've got the matrix like this, we can now ask what's happening at time t equals 2, and that would be x of 2 is going to be p times x of 1. Okay? And then that is P, our transition matrix. This matrix does not change. And then we multiply by x of 1, which we've previously figured out to be this guy here. And we do that multiplication, and I got these numbers here. Okay. This means there's a 52% chance he'll be in reserve 1, a 24% chance he'll be in reserve 2, and a 24% chance he'll be in reserve 3. Okay, of course, now I can keep going. I can compute x of 3. Now, let's just write out symbolically what x of 3 looks like. That's going to be p times x of 2. But x of 2 is p times x of 1. And what is x of 1? Well, x of 1 is p times x of 0. So we see that x of 3 is p times p cubed times x of 0. Again, there's an obvious reason why we're talking about powers of matrices, diagonalizing and be able to find powers of matrices. Okay, so I wanted to know what the probability of the line being in the 3 reserves at time 3. I don't actually have to calculate time 1 and time 2. I simply have to take the initial state that I was given and multiply it by the cubed power of the transition matrix. Let me just imagine us keeping going, and let me just write down some numbers here. I've made this calculation, x of 6. So this is going to be p to the 6 times x of 0. And that works out to be this thing here. There it is. Okay, now I think an obvious question to ask is, well, at some point, is this just become a steady state? And the answer is yes, and we're going to see what the conditions are for that. So this is a steady state. So after some amount of time goes by, this is, no matter how many more times you multiply by p, this is going to stay the same. So the question is this a steady state? Is this a steady state? And the answer is yes. Yes. Okay. And this is just what I did above, right? X of k. This is just x of k, which I've been writing like this actually. X of k is p to the k x of 0. Okay, that's the general case. So we definitely need to take the matrix power. Okay, so we just need a little bit of certainty on the transition matrix. It's actually a fairly minor constraint, but so that we will know that we actually do reach a steady state. And what we need for that is the stochastic matrix to be regular. The definition of regular is that the matrix itself or some positive power of it has all positive entries. So positive means greater than 0 and not including 0. We're not going to have negative entries anyhow, because that doesn't make sense for a probability, but we could have a probability of 0. So we have to watch the zeros is what this is saying. So let's just look at the wildlife transition matrix we just had and ask ourselves if it's regular. Okay, so we have if, okay, when I look at this, I'm like, here we have P. P has all positive entries. This is regular. Yes, it is regular. Okay, let's try another one. Here's a matrix P. Now, P has, these both add up to 1. Now, column vectors are probability vectors, but we have these zeros here. These are not positive. So P itself does not have all positive entries. Okay, so what we have to do then is start checking the powers. Because it will be regular if at some point by taking powers of P, the entries become positive. Okay, so we're going to check the powers of P. In this case, what we would do then is calculate first P squared. We would get this. And that gives us this guy here. Then we would calculate p cubed. We would take p squared, multiply it by p. And that would give this guy here. Okay, and I already know what happens actually when I multiply this guy by p, because I've already done that here. So I'm just going to flip flop back and forth. So these zeros are going to stay. I'm never going to get non-zero entries here and here. I'm not. Okay, so this is not regular. This doesn't always happen when there's a zero. Let me just give you another example where it doesn't happen. So let's contrast with this. We got this guy here. Okay, let's just call this guy P now. And when we look at this, we're like, okay, it's not necessarily regular as of yet. We don't know because of this zero. So we have to see after we start taking powers, will that zero disappear and become positive? Okay, now let's just do P squared. And I get this matrix here. Okay. Well, no. All of these guys are positive, so this guy is regular. Once you've got all positive entries, and now I'm like p cubed, I would be taking p squared, this guy here, multiplied by this, right? There's no way of getting back to any zeros but coming back. Like once the zeros disappear, they don't return because the entries are positive. Okay, so we don't have to, once we get to a certain power and the zeros have disappeared, then we're like, it's regular, and we stop. Okay, so that we need that because if we want to know what the long-term behavior is of a Markov chain, we need that it's regular. It's not much of an onerous restriction. Usually there aren't even any zeros because we don't often have probability zero events, but it is of course possible. Okay, so what this theorem is telling us is that if we have a transition matrix for a regular Markov chain, then there is some vector q, a unique probability vector q, such that PQ is equal to Q. It means that after some amount of time, even though you keep reapplying the transition matrix, the vector doesn't change. You've reached a steady state and nothing is going to change. Okay. This is when things do not change. You could be looking at this and saying, oh, we've seen this before. This looks like the equation for, it is the equation for finding, for when lambda equals 1 is an eigenvalue. Okay, it's a fixed point. Okay, so under this case, if we keep taking powers of that transition matrix and multiply it by our initial state, we are guaranteed that the thing will converge to this steady state vector Q as k heads to infinity. Okay, it's a fixed point. It's the eigenvector when lambda equals 1 is the eigenvalue. And we find it in exactly the same way. This is the equation for the matrix that you, well, this is the matrix that you row reduce to find the eigenvectors when the eigenvalue is 1. So let's compute what this Q is for the matrix that we've used so far. Okay, so I'm going to take I minus P, and I get the matrix 0.5 minus 0.4 minus 0.6 minus 0.2, 0.8 minus 0.3 minus 0.3 minus 0.4 and 0.9. Okay, that's 1 minus 0.5, 1 minus 0.2, and 1 minus So those numbers there, 1 minus 0.9, and the other numbers have negative signs on them. Okay, now I want to know for this matrix here, this matrix, for what values, what I want to solve the AX equals 0. This is a AX equals 0 problem right here. What is the solution to the homogeneous system for this guy right here? So I go ahead and I do the usual thing here. I'm asking you to do this. You can augment it with like that if you like, and then you do the row reduction and you solve for the values of Q. And I will simply write down the result here. You get this Q, it will be T times, this is what I got, 15 over 8, 27 over 32, and 1. Okay, now I'm going to select T. I want this to be a probability vector. So I'm going to select T such that the total 15 over 8 plus 27 over 32 plus 1 times T is equal to 1. I want to make sure that this is a probability vector. So I go ahead and do that. I find that value of T and I rewrite Q as this vector here. Because this is basically the eigenvector for eigenvalue of 1, the steady state solution when nothing is changing, no scaling, nothing is changing. I get those numbers. Now, what's very exciting, folks, is look at what X6 was from before. I'm flipping back in my notes to make sure that I copy it out correctly. I calculated X6 before by calculating what? P to the 6 times X naught, where X naught was a probability vector that looked like that. The line was in reserve 2. Then I calculated P6 and P6 times X naught, and I found this to be equal to this. There. Okay, and it's the same to sort of any sort of computational error that I may have. So, and these numbers here, given my value of T, can be made exact, right? This is an eigenvector effectively. And here, what we did is we used what is effectively a power method to find the dominant eigenvector in this case, which we basically assumed was 1, right? We just took the dominant eigenvalue is 1. So here, what we're doing is we're simply taking the transition matrix, taking it to a large power, multiplying it by the initial state, and that gives us the steady state solution. That same steady state solution can be found by using the methods of eigenvalues and eigenvectors from before. Okay, so this is yet a second example. So we saw if we have a matrix A, we have reason to want to find these sort of things. Okay, we have reason that we want to find large powers of matrices. We saw that in the power method, and now we're seeing this here in a very similar context with the Markov chain, and under certain conditions of what the matrix A looks like, we get a steady state. We find the steady state solution of the dynamical system. So the diagonalization comes in here in order for us to be able to effectively make these calculations. That's it. Applications of diagonalization. Thank you very much, and we'll be back with section 7.1 shortly. Thank you.